Swayam Prabha. Digital India. Educated India.
Welcome to lecture number 19, part 1. The topic of this lecture is food deterioration models and shelf life testing. So, the food deterioration models are these mathematical equations, a set of empirical relations or mathematical equations. They are primarily used to predict the quality of the food, like how long a food product can remain safe for consumption. So, these are mathematical equations to predict how long the food product remains safe. Food product remains safe and meet quality standard. So, as we have seen in the previous lecture, that is lecture 18 part 2, so we have seen the two types of factors, intrinsic factors and extrinsic factors. 4 to 5 factors under intrinsic and under extrinsic factors, which would affect the shelf life of the product. So, various factors such as processing, packaging, storage condition. So, these are all the factors which would be used or to evaluate the stability of the product. So, how long the food product can remain safe for consumption. So, that is the primary objective of having these models, mathematical models. Of course, it is used to predict the shelf life and optimize the processing parameters. Yes, to predict the shelf life. There are two types of shelf life stability test. One is real time, another one is accelerated. Or let me explain, then we'll. So, in the real time stability test, as the name indicates real time, in reality, the product is stored under recommended storage condition. The storage condition varies from one product to another product. So, whatever for the recommended storage condition, the product is stored until it fails. Suppose if a product takes, say, for example, 30 days, it is stored and it is monitored periodically or regularly until it fails completely. This process, normally it's a time consuming process. It takes longer time, because suppose if the shelf life of a product is, say, 180 days, which is about 6 months. So, the stability test normally it takes lot of time. It's a time consuming process. So, it varies from one product to another product. Though this process takes a longer time, a longer duration, it is accurate. It is accurate compared to accelerated stability test. So, it is accurate. This method is accurate as the analysis of the test gives the actual degradation or the quality deterioration of the food product under storage condition. So, the second test is the accelerated stability test. So, as the name indicates, here the food product is subjected to an accelerated environment. How we can have the accelerated environment? By increasing the rate of decomposition. Which can be increased by increasing the temperature of the reaction, the chemical reaction. So, this test is conducted in an artificially created environment. It is not done in a natural storage condition. An artificial environment, an accelerated environment is created by the increasing the rate of decomposition, and the product failure rate is monitored. Product failure rate is monitored. So it is a faster process, much faster compared to the real-time stability test, but it is not accurate. We have already seen the factors which affect the quality of the food or the deterioration, microbial growth, the presence of microorganisms such as bacteria, mold, fungi, yeast, etc. These are all the various microorganisms which affect the quality of the food, number one. Enzymatic reactions, that is the biological reactions. Chemical reactions. Under chemical reaction, we have the oxidation and hydrolysis. We have seen in the extrinsic factors affecting the shelf life, the packaging, the presence of gases. If oxygen is there, it promotes the microbial growth under the packaging. And instead of oxygen, if you have carbon dioxide, like a modified atmosphere, right? We have a modified atmosphere packaging. So where the CO2, if CO2 is there, the concentration of CO2 is more. CO2 prevents or reduces the microbial growth when it comes to the packaging. Hydrolysis. Here I have mentioned about a process called hydrolysis. It's a chemical process which is used to break down a molecule with the help of water. So let me write this one, hydrolysis, here, since there is some space here. Or let me see where some kinetic models. Okay, I will write it here itself. Hydrolysis. I'll give one simple example. Suppose if you have a reactant XY, okay, so it reacts with water molecule and X. The H2O is split into H plus and OH minus plus YOH. YOH. So it's a chemical process during which water is used to break down a molecule. So here XY is split into X and Y. Water molecule is split into H plus and OH minus. So this is an example of hydrolysis process. And of course, we have seen under the physical changes, here I have mentioned temperature, moisture content. We have seen this in the extrinsic property, extrinsic factors. The factors which affects the shelf life of the product, which are external in nature, which are outside the food product, We have seen the storage temperature, how does it impact. Low temperature reduces the microbial growth. Freezing prevents microbial growth. However, but some microorganisms still grow even under frozen conditions. Similarly, the moisture content, I had mentioned about the humidity, the relative humidity, which is expressed as percentage. Higher humid environment, that is promote microbial growth. Low humid environment, it reduces or prevents the microbial growth. So some of the points which I have mentioned in this slide, we have already discussed. I have explained in under the factors affecting the shelf life. Let us see the different types of food deterioration models. Kinetic model, Q10 model, time temperature tolerance model. It is called T model. So let me explain each model. First, let us see the kinetic model. Whether it is a kinetic model or temperature time distribution model or Q10 model, generally these models, these are used to assess the quality of the product. How long a food item or food product takes for to get deteriorated. So these models describe the rate of chemical reaction. They describe the rate of chemical reactions and microbial growth that affects the food quality. Primarily, these models are set of mathematical equations or empirical relations, as I have mentioned before, to predict how food quality changes over time, whether the quality of the food product gets affected in 10 days or 15 days or 6 months, depending upon the nature of the food product. So these are all these models uses mathematical equations to predict the quality of food with respect to time under specified conditions. What are the conditions? That is under the storage, temperature and time. Storage, temperature and time. These models helps to optimize the processing parameters, processing techniques and the storage condition. So the primary objective of this model is to eliminate the food loss or wastage or getting the food getting spoiled. So, or to minimize, we cannot completely eliminate these losses. However, these models help us to reduce or minimize the food wastage or food spoilage. There are three types of kinetic models: zero order, first order and Arrhenius model. We will see one by one. Zero order kinetics. So the rate of reaction. So here the rate of reaction is equal to the rate constant. So the rate of reaction is directly proportional or equal to the rate constant. Rate constant is K. This is the rate constant. Okay, this is the rate constant. So it is the reaction rate is independent of the concentration of the reactant. So the mathematical expression of this one is minus dCA by dt is equal to K into Ca power n. This is the general equation where A is the concentration of the reactant, K is the rate constant and n is the reaction order. If it is a zero order reaction, n is equal to 0. If it is a first order reaction, n is equal to 1. So let me write this equation. Kinetic models, zero order reaction. First one is zero order reaction minus dCA by dt is equal to, let me write the equation, K into Ca power n. Let me again emphasize, n is the reaction order, K is the rate constant and A is the concentration of the reactant. So this is the general equation. Let me write it here. This is the general equation. For a zero order reaction, n is equal to 0. The reaction order is equal to 0. So let us take this as equation number 1. Therefore, equation 1 becomes minus dCA by dt equal to K into Ca power anything to the power 0 is 1. So this is equal to K. So that's what I have mentioned here. minus dCA by dt equal to k. This is equal to k. So we can bring this k to the dt to the right side and integrate. So that is minus d into Ca is equal to k into dt. So this is equation number 2. Equation number 2. Integrate equation 2 between the limits t equal to 0 and t equal to t. This is the time. So we will get, this is k into dt. This will become integral of dt is t. So Ca minus Ca0 equal to k into t. Let me check. Ca minus Ca0 equal to minus, of course, minus sign will be there. This minus sign I will bring it to that side. So this is equal to, this minus will be there. And when it goes there, that's it. Therefore, Ca minus Ca0 equal to minus kt. From this we can find C suffix A, which is equal to CaO minus kt. Okay, so that's what I have got here. Ca equal to CaO minus kt. So here I have mentioned the SI unit for K, that is the reaction rate. Reaction rate. SI unit for K is, SI unit for K for a zero order reaction is moles per second. Moles per second. Let us move to the second kinetic model, which is the first order kinetics. So this is first order kinetics. This is zero order kinetics. That is first order kinetics. So again, let us take the basic equation, minus dCA by dt equal to, for first order kinetics, the reaction order is n is equal to 1. N is equal to 1. Therefore, minus dCA by dt equal to k into Ca power 1. Ca power 1. So this will be equation number 3. Equation number, substitute n is equal to 1 here. So it will become, the right hand side will become k into Ca power 1, that is k into Ca. Now integrate equation 3 between the limits time t equal to 0 and t equal to t. So before that, let me rearrange this one. Minus dCA by Ca is equal to k into dt. So this will be equation number 3. This will be equation number, integrate equation 3. So left hand side will get integral dx by x is ln x. So like that, ln of Ca equal to integral dt is t, k into t, k into, so k into t, ln of Ca. Let us, limits is from t equal to 0, t equal to t. So t minus 0 is t, right hand side. So this will be minus dCA. Yes, minus dCA. So apply the limits. So that will be ln of Ca. Let me check. Ln of Ca by Ca naught. Ln of Ca by the time limits are T equal to 0 and T equal to T. These are all the limits. CA by CA 0. That is equal to K into T. So, the SI unit for the rate constant K for a first order reaction is per second. Whereas for zero order, it is moles per second. Moles per second. The third model, which comes under the kinetic model, is Arrhenius model. Arrhenius model. So, it describes the temperature dependence of the reaction rate. It describes the temperature. Let me change the pen color. It describes the temperature dependence of the reaction rate. So, the mathematical equation which is used to predict the food deterioration in this model is K equal to A into E power minus capital E by RT, where K is the reaction rate constant per mole per second. That is the unit for rate constant in this model. A is the frequency factor, which is also called as pre-exponential factor. Capital E is the activation energy expressed in joules per mole, and R is the universal gas constant, that is 8.314 joule per mole Kelvin, and T is the absolute temperature in Kelvin. So, this is Arrhenius model. K equal to A into E power. This is the equation. So, let us solve one small numerical question before I conclude this lecture. In case if there's time, we will see some more numerical question. Otherwise, I will be continuing in lecture number 19 part. So, the activation energy of a chemical reaction is 100 kilojoule per mole, and its frequency factor is 10 mole per second. So, this is per mole per second. Okay. So, this capital M denotes mole. Find the rate constant of the equation at a temperature of 27. So, activation energy, that is activation energy is E is given. It is given as 100 kilojoule per activation energy. Capital E is equal to 100 kilojoules per mole. Frequency factor is given. This is capital A. Let us see frequency factor is capital A. This numerical question is based on the Arrhenius model. Frequency factor. Let me write it again. Frequency factor capital A equal to 10 M minus 1 S minus 1. That is, it is nothing but mole per second. That is the meaning. In some textbook, they use capital M power minus 1, that is per mole. The temperature is given 27 degrees centigrade. So, add 273, 300 Kelvin. So, based on the data given, the activation energy frequency factor. So, this numerical question is based on Arrhenius model. So, I will be using the equation K equal to A into E power. So, according to Arrhenius model, K is equal to A into E power minus capital E by RT. So, we have to find out, if you see the question, find the rate constant. Find the rate constant. Rate constant is K. Rate constant is K. Rate constant is K. So we have to find out K. So A is given, capital E is given, temperature is given, R is 8.314. R is, if it is not given, you have to take this value, R equal to 8.314. Okay. 8.314 joule per mole Kelvin. Okay, so there is this value. If it is not given, always we have to take this one. Universal gas constant. Joule per mole Kelvin. So substitute the values. K is equal to, substituting the values, K is equal to A is 10. Let me write it here. K is equal to 10 small e power minus, that is in 100 kilojoule, divided by R is 8.314 into temperature is in Kelvin, so 300. So that's what I have substituted here. Okay. Activation energy will substitute in joule. Okay, because the numerator, this is in joule per mole Kelvin. So this 100 into 10 power 3 joule per mole. Because it is given in kilojoule, so this is 100 into 10 power 3. So solving, you will get the rate constant as 3.87 into 10 power minus 17. 3.87 into 10 power minus 17 mole per second. That is nothing but capital M minus 1 S minus. So it's a very small problem. So let me stop this lecture number 19 part 1 at this point. Thank you. I will be continuing some more topics, numerical questions in lecture number 19 part 2. Thank you.